Okay, I can see the attendees pouring in, so we'll make a start. Good afternoon and welcome to this UKIVA Roundtable webinar on machine vision trends and technologies. My name is Warren Clark, publisher and founding editor of Imaging and Machine Vision Europe magazine, and I'll be moderating this afternoon's session. Before we get started, a few housekeeping notes. The session is being recorded and will be available on demand via the UKIVA website later. As attendees, you've all been muted. However, you can still get involved by posting a question to our panel using the Q&A function at the bottom of your screens. There's also a chat function for comments and connecting with fellow attendees, but please refrain from using this for company promotional purposes or posting URLs. Finally, once we've ended the session, you'll see a link to a post-event survey. Please take a moment to fill it in and help us improve future events. So, let me introduce you to our stellar panel of experts who are going to take us on a whistle-stop tour of the most notable technologies and trends in machine vision. Joining us today are Mark Williamson, Managing Director of Stemmer Imaging UK, Dr. Boris Langer, Imaging Business and Business Development at Edmund Optics, Carsten Trauper, Director of Product Management at IDS, Sean Wood, UK and Ireland Sales Director at Clearview Imaging, Ian Alderton, Technical Sales Director at Allrad Imaging, and finally Neil Sandhu, who, as well as being Machine Vision Product Manager at SICK UK, is also the current UKIVA Chair and has coordinated today's panelists. We're going to spend the next 45 minutes or so touching on 6 key topics in machine vision. We'll look at vision in robotics, at deep learning and embedded vision, 3D vision, systems and applications, camera technology, and finally optics and illumination. Neil, let's start with you on the topic of vision in robotics. What factors have played a part in making this a fast-growing sector recently?
Thanks, Warren, and hello everybody from me. Great to be here. That's a really good question there in terms of how the coexistence of robotics and machine vision has come on leaps and bounds in recent developments and recent times. Gone are the days. I mean, I've been in vision for about 20 odd years, so I don't know everything, but I know a reasonable amount. And gone are the days, I would say, when you get your vision system sorted out and then, oh, now I've got to sort out the communications to the robot and making sure it talks to the robot in the right kind of language. With recent work that's been done between the machine vision companies themselves, as well as the robot manufacturers, that whole tie-in regarding making sure that the machine vision system talks to the robot and vice versa, a lot of that pre-work has been done because of the collaboration between machine vision companies and robotics companies. So much so, pre-written drivers, clicking a drop-down within the vision system configuration interface to say I'm working with robot A or robot B is now all it takes at times to make sure this communication works brilliantly. Secondly, the fact that the information can be sent out, received from the vision system. Let's talk about guidance, so your positional information of an object to pick up, let's say. All of that now can be sent out at a very rapid rate using standard communication protocols that the robot understands to make sure cycle times are improved, as well as the efficiency of the application. And the final quick point I'll make on this to answer this initial question is the advancements in technology. We're going to hear possibly later on about the advances in 3D technology, but with newer 3D technologies like time of flight and stereo vision, the ability to get the information needed from a 3-dimensional space or scene, analyze it, and get the required information to the robot happens very quickly and very simply indeed.
Great stuff. We talked a little bit about common coordinate systems. Is that covering what you've already spoken about, or is that something slightly different?
That's on the same level. It's a really critical point that the camera, those of you who are obviously aware of vision systems, has its own field of view, and the robot has its own 3-dimensional space that it works in. And so to get one to work with the other used to be a little bit of a pain to make sure that the point in space that the camera sees can be transformed so the robot understands that same point in space to go and either pick something up or put something down. But now, again, because of the technology that's been developed recently, the ability to put even a simple target in front of a camera, and the camera then understands the coordinate system, and then for the robot to be driven to, with, let's say, just a few points within that target, it understands and completely amalgamates one coordinate system to another, so it understands the two working spaces as one. And that all happens, again, in a very, very simple way nowadays, thanks to the advancements in this technology.
Great. Okay, thanks. Boris, can I bring you in now? Maybe look at this from an optics point of view. So presumably moving around on robots creates very specific challenges for optics.
Yes, that's certainly true. First of all, hi everyone. Great pleasure to be here with you today. So yeah, coming back to the robots, absolutely, it has huge implications, especially on the optomechanical design, right? A normal lens, you can have that standard focus mechanism, you can have that iris lock, you can have the iris itself, right? If you think of these elements in an optomechanical design and you put them all of a sudden in this harsh environment with vibrations, with mechanical shocks going on, these things will fall apart, right? So instead of the iris, you need a fixed aperture, for example, instead of a floating element focusing design, which is a little bit more advanced. Actually, it's not suitable anymore all of a sudden, because at the end of the day, it's not even more about the optics do not only need to survive in these environments, it's really very closely related to what Neil was just saying about these two different coordinate systems. You know, these coordinate systems must match not only today, but also next week. And so the optics play a major part in that game. Just they need to be able to map the world and map each part of the world to the same pixels now and after the robot has been moving for an hour and 4 weeks. And yeah, so that you need to put glue in place, you need to think about different focus locking mechanisms, all sorts of good stuff and fun that we're happily worked on over the last years, especially.
Great. Okay, thanks. Just a reminder to that the questions, you can ask a question at any time, and we're going to move through these topics pretty rapidly. So do ask a question at any time as we get through them. We're going to move on now to deep learning and embedded vision, which have become very much the buzz phrases within machine vision in recent years. Carsten, can we come to you on this one? So can you maybe give us some examples of the types of applications where deep learning can make a difference?
Yeah, thanks. Also, hello to everyone from my side. Basically, applications benefiting most from deep learning are applications where you have to deal with detecting or classifying irregular or complex forms, typically stemming from the organic area like plants or fruits. Also irregular defects on surfaces where you do not really know which kind of shape they will have from the beginning. For example, we've seen very successful implementations of deep learning dealing in the horticulture area, where you want to classify the ripeness of plants prior to harvesting them or to harvest them at the right time, doing quality inspection in fruit sorting or food processing. But also we've seen successful applications of deep learning in inspection of unstructured substances like foams or pastes. So basically all kind of patterns or schemes which do not follow a defined mathematical structure. And so to say, you can, with deep learning, you can enter areas which have formerly been unsolvable or nearly impossible to solve with traditional algorithms. And this brings me to the point of, will there be a kind of a coexistence or kind of overlap between deep learning and traditional algorithms we've all been used to from the past? And for me, clearly, deep learning will be no replacement for traditional algorithms, but they will really complement each other. And they even often will be used in combination. So let me give some examples. We'll see classification as a starting point from a deep learning perspective. And then once you classify the object, you choose the right CAD model for this substance or this object you detected to do, let's say, a gripping of a robot or something like this. Or you have a larger picture where in an uncontrolled manner, objects are lying around and you need an object detection first to find the object. And then in the bounding box the deep learning gives you, you would then apply traditional algorithms like an edge detection or something like this. I think building on this, a lot of customers still shy away from using deep learning because somehow people tend to tell them it's complicated to implement deep learning systems or algorithms, and I think that's the software developers paradigm, to develop everything by themselves from ground up. But I think we've moved beyond this in our industries, because they are ready to run tested, predefined deep learning algorithms available out of the box, where the customers who kind of intend to apply deep learning, where they easily can do this without having to become experts in deep learning implementation, but they can just stay domain experts in their application area where they come from with their industry, and without having to program this stuff from the ground up. Thank you.
Okay, thanks. If Mark, maybe we can bring in, and Carsten's touched on a little bit of this already, but deep learning and embedded vision have become buzz phrases, but to a certain extent, are they new names for old tech, if you like? And they're also talked about in the same breath. Are they linked? Do they sort of work together?
Hi everybody. Great to be here. I think that the first thing to say is they are separate things, but deep learning and embedded vision are often used in some of these new emerging applications. So if we look at deep learning, the first smart camera, embedded vision. If we start with embedded vision, the first smart camera was in fact an embedded vision. It's got a processor, a sensor. That's what an embedded vision system is. What you've effectively got with the new buzzword embedded vision is there are standards and tools coming out to enable you to build your own embedded vision system. So what is an embedded vision system? Generally low power, small. People jump on the bandwagon and say, oh, it's low cost, Raspberry Pi, things like this. However, it's still true that the development time to create something embedded is massively higher than a PC-based system. So unless you're using a smart camera where it has all the software written and everything done, to develop your own embedded vision systems is a lot more difficult. But one of the things that Carsten mentioned on deep learning is it's opening up new applications. So if you look at embedded vision, look at car self-driving and stuff like that, high power, lots of processing energy to recognize common things. And that's where deep learning started. Google with its face recognition, cat, dog kind of recognition, where they could teach thousands and thousands of images to create very robust deep learning from scratch. And that was the blockage for industrial applications. You don't have thousands and thousands of examples of defects. So you have to be able to reduce it down. So all the work's gone in to reduce it down so you can start to teach things with 20 images, 30 images, stuff like that. You still have to be thinking carefully about negative instances, positive instances. You still need to understand the domain and what's varying. You can't just teach it loads of different things and expect it to work, but it's massively easier. Okay, so deep learning is actually a buzzword that's come out, which really covers a wider area called machine learning that has been around for 20 or 30 years. The big thing with deep learning now is that it's using it's in machine vision. It's been made to be a lot easier to use, small feature sets. It still often needs a lot of processing power to work, but that's being overcome step by step as well. And I think what also we're now seeing, the big development in deep learning isn't just classification, which was the traditional starting point, but it's now things like anomaly detection. So you basically teach it all good things and it will start to say, this might be different, this might be a defect, this might be a defect. It's always very difficult to say, show me 30 examples of that defect. In a production line, that might take you a year to get to it because they're all slightly different. They're all variations. So the three A's, obviously recognition and detection of where something is in position, which is a deep learning application, classification of what type of object it is one, and then the anomaly detection is the new thing that's coming out, which is pretty powerful.
Okay, great, thanks. We talked about buzz phrases. I guess if we'd have had this discussion a decade or so ago, then the buzz phrase would have been 3D vision. So let's maybe go to Ian on this first. So if we're talking about 3D vision, there's been an increase in the use of structured light in triangulation systems. How does that work and what benefits can it bring?
Right. Hi, everybody. The 3D vision, or there's some of the other techniques you say stereo 3D time of flight. So stereo vision started with 2 cameras and you were looking at it, perhaps either side of an object like a saw that was cutting something so you could see where you were going, but there wasn't really much depth or height perception in that or any measurement. With structured light, you then had a laser line or multiple lines in a field of view, and with a fixed lens and working distance, you could then work out distances. You could actually calibrate a system. So when your object then moved, you could work out the number of pixels, which would give you a result in millimeters or whatever measurement system you've set up in both directions, and calibrate. So you get a calibrated reading out of the moving object. So that's basically how it works.
Okay, and then there's also been developments in software, which opens up possibilities there as part of that. Is that true?
Yeah, the software is developed, and you can also do it on graphic generators, GPUs, and everything else. So you can get it more easily calibrated. And then there's time of flight type bits as well, which is a different technique.
Okay, sure. Maybe can we bring you in, our last panelist today? So what other 3D techniques are available, and to which applications is 3D vision most suited these days?
Yeah, thanks. Hi guys, great to be here. So I think it builds on what Neil and Ian have said, right? 3D technology hardware has evolved greatly over the last 5 or 6 years, and as the technology improves, so too the applicable applications. So stereo, time of flight, laser triangulation, and structured light fundamentally rely still, other than time of flight, on 2D sensors. So as resolution, frame rate, data throughputs increase, so does the accuracy and speed of the 3D vision systems. Time of flight is a really good example of how quickly that's moved. If you looked at time of flight of even 3 or 4 years ago, it just didn't have the accuracy required to be considered an industrial means of carrying out a 3D application. And then the work that Sony have done with the depth sensors means it's now perfectly accurate enough in robotic pick and place to identify objects to within a millimeter for a robot to go and pick. In terms of the applications, Neil mentioned at the beginning there the guidance of both robotics and automated vehicles are really driving the development of 3D technology. In the UK, we're lucky to have some of the real early startups around driverless cars, and 3D stereo vision is used extensively in those type of applications, along with lots of other sensor technology. In agri-tech, 3D is being used not only for guidance, but also for crop recognition and detection and analysis, and that's a huge growth area for that technology. And then we're seeing time of flight being used in some more novel applications around gaming and reality, augmented reality type applications as well. So a real varied board of applications now.
Okay, and when we spoke the other day, we mentioned point clouds as well as a methodology. Can you maybe talk a bit more about that?
Yeah, so look, point clouds are one of the varieties of standard outputs from a 3D sensor. There's line profiles with triangulation that Ian mentioned, and then there's depth maps, range maps, and point clouds. I think Neil probably touched on the biggest development in that area is the standardization of that output format and the ease of ingestion into third-party libraries now. 3D used to be quite painful to set up once you considered calibration and then being able to work with the data output. Advances in calibration and then standardization of the data output and ingestion has really made that more of a plug-and-play application now.
Okay, thanks. Okay, we're around halfway through our kind of pre-arranged topics, so just a reminder that you can ask questions anytime. We've had a couple of questions come in already. Thanks for those, and we'll return to those questions once we've rattled through our pre-arranged topics. Let's turn our attention now to optics and illumination, and to our optics expert, Boris. What can you tell us about the latest developments in optics and lenses for machine vision?
Yeah, sure. There's a whole bunch of things going on. They might not be present as all the big buzzwords we already heard. They're one step behind, I guess, the system level topics. But there's certainly a lot of interesting things going on. There's the ever ongoing megapixel race. There's this whole notion of extending the waveband to the UV to short wavelength infrared. There's another evergreen would be liquid lenses, ruggedization of imaging lenses, as we already talked, which is important for 3D and robotics. So yeah, then maybe last thing to note is this EMVA initiative. There's a bunch of guys over at the EMVA that are working on standardization process how lenses can communicate with cameras, and this is going to enable computational imaging. So yeah, this is just what comes to mind first. I mean, I could probably go on and on, but I think I'll just stop it here. Pick anything you want to hear more in more detail.
Let's see if there's any questions asking you to go on. Yeah, Boris, we'll come back to that.
Absolutely.
Okay. So another critical aspect of the machine vision setup is illumination. So let's go to Mark on this one. What can you tell us about developments there?
Hi. Well, obviously, illumination has always been critical for a machine vision system. Very often it's underestimated, but the whole thing, certainly with traditional machine vision, or even with deep learning, you have to teach all the variations of light. So to make something work best, it's good to control the environment. Also, quite often you can see things with a certain type of illumination, low angle, high angle, whatever. That's all fairly well known within the community. But what's really come along in the last year or so is and it was mentioned by Boris, is computational imaging. And that's where by taking a number of different images that either have different illumination setups or maybe a different focus, for instance, in the lens or something like this, you can actually start to identify additional information. So technologies such as what's called shape from shading is a very good one, where you have 4 different angles of illumination and you can almost start to get micrometer 3D data just by the illumination, and so grab 4 images, process it using this special algorithm, and you get new data out. So that, I think, has been one of the main areas of illumination. But also we are seeing things like cloudy day, cloudy day isn't illumination, but natural light. LEDs have become very much a important way of using illumination, because halogen, they don't last very long. In industrial people, they want them to last, so LEDs come along. But LEDs had a very spiky illumination, which means it's not so good at true color and stuff like this. So there has been a developments where actually certain kinds of coatings, etc., start to give a very better even illumination in daylight, and that's also then being extended beyond the visible into the near IR and up to 1700 nanometers. And why that's important is, that is what's called hyperspectral imaging. And obviously hyperspectral imaging is effectively you measure the the output at different frequencies, and you can start to see things like bruising in fruit that you can't humanly see at all with a normal visible camera. You can start to see that, and traditionally the only way to do it was with halogen lighting. And LED lighting in the last, I say, 18 months, we've started, and each iteration gets better and better and better. The output gets stronger, more powerful, so you can start to apply LED technology into those areas. So it looks as if it's not changing. All the standard ring lights and all of that are still there. I suppose the other thing I would say is a lot of intelligence is going into the lights now. So they have integrated strobe controllers in some of them now to make integration easier. And we've actually started to see lighting controllers that actually support the GeniCam standard, so you can start to control them natively from any GeniCam compliant software. So lots of things happening, and I think the message across everyone, there's a big push for ease of use and making stuff easier to use.
Great. Okay, thank you. Let's move on to camera technology now, and we'll go back to Ian for this one. So we're on the verge of 25 gigi in terms of future technology, but in reality, we're only just into the age of deployed 10 gigi, aren't we? Is there a reason for that? Does this take a while to come on board?
Yes, well, believe it or not, 10 gigi was introduced in 2010, and we've 25 gigi was introduced in 2018, and now 2021, 100 gigi has been introduced. But with that, you have the specialist SDK required to drive the cameras, and the applications, they all tend to be on the leading edge. So it's researchers and R&D type bit. And then as time develops and techniques get introduced and more standards become, then they become deployable in real world applications. So it's accelerating, as everybody says, because it's taken, what, 10 years from the 10 gig standard coming out to it starting to be deployed in more standard applications rather than pure research. But the research will always be ahead. The advanced features will always be only available with the specialist network interface cards, NIC cards, or the specialist SDK with the cameras that the camera manufacturers do. And it's only with standards that they become more easily usable and deployable in all systems.
Okay, thanks. Sean, kind of following on from that, what lessons have been learned through the development and deployment of 10 gig E, and what will limit future developments? Ian's touched on a couple there, I think, already.
Yeah, I think Ian's probably covered where we are with 10 gig E. If we look at the innovation adoption curve with 25 gig E, certainly the early adopters are starting to work with that. But in terms of 10 gig E, we haven't peaked at the majority use case yet, I think, and part of that process means that we're still learning. So 10 gig E was slow to uptake as a true machine vision standard, but it's really gained traction recently, initially with core machine vision users, high resolution line scan, high resolution area scan applications where you want the simplicity of the cabling and a low cost NIC and the GennyCam standard. But more recently, we're seeing use cases where customers within the sports analysis or augmented reality sector are turning to 10 gig E to run 4K cameras at 60 frames a second plus, and to take 20 or 30 of these cameras back into a CPU hub to then process in real time. And we're learning through those applications that although officially there is no frame grabber function required to run a 10 gig E camera, the CPU load required to receive, unpack and display this amount of data in real time is making hardware manufacturers look again at providing some offload capability on these NICs. And I think the next wave of kind of technology to be released within 10 gig E will be NICs with offload. So fundamentally frame grabbers that can do some pre-processing before putting this off onto the CPU. I think as we look at 25 gig E and beyond, that's going to absolutely be a requirement. So the work that's been undertaken with 10 gig E now, I think, will shorten that cycle when 25 gig E becomes more mainstream.
Okay, Ian, did you want to sort of follow up on the CXP and frame grabbers there?
Yeah, I mean, apart from the gig E field, there is also other work going on with frame grabber based technology using Coax Express for digital data with multi-lanes at high speed, again for the higher resolution, high data rates. So that it isn't all in the 10 gig E, 25 gig E ballpark. There is other competing technologies. We'll see what happens in the future.
Okay, great. Okay, finally on our sort of pre-written topics then, let's look to sort of systems and applications. So rather than being seen as a standalone solution, machine vision fits into the broader context of, for example, the entire manufacturing process. So Carsten, if we can come back to you for this one, to what extent do vision system integrators need to be aware of how their systems will fit into and work with the whole manufacturing process?
Yeah, I mean, as Mark already explained, with embedded vision, we are moving from an engineered, I would call it, to a designed system approach, meaning that we'll have with embedded vision, we'll have this compactified vision system where you formerly had a camera, PC, cables and everything into one housing, getting smaller and smaller. And basically, in this area, you will see, or you will start to look at a vision system as a sensor in a manufacturing environment, like any other sensor, like a temperature sensor, a pressure sensor, which it's just doing its job. It's maybe intrinsically a little bit more complex, but in the end, from a factory automation perspective, it's delivering data to an automation controller. It's a good or a bad piece that is the size and whatnot. And from this perspective, together with this seen as a vision sensor with dramatically reduced cost and with an increased ease of handling. For the vision system makers comes the burden to really understand what it means to integrate into factory automation. And basically, there are standards which we sometimes overlook, but they will become more and more important for the future. There is Profinet, OPC UA as really standardized languages, how within the factory automation environment, the different devices speak. There is the REST protocol, a little bit more generic in the Internet of Things area, but also important in this sense. And the vision system makers, they need to learn to be conformant to these standards to allow a kind of a plug and play approach into the factory automation world. And with working out of the box in a standardized and certifiable way. So in the end, we as an industry, when we say we as the machine vision industry, we have to humbly learn what it means to integrate into these larger systems and become part of this as a standard, because I think it will be in the end a tremendous benefit and to be just plug and play in this world, yeah, and working out of the box in a predefined way in factory automation. So this is what I call the vision sensor approach, moving away from this engineered looking inside and its complexity towards looking to the outside, talking through standardized interfaces to the factory automation world.
Okay, thank you. Neil, if we can bring you back in for this one as well. So can you give us some examples of where we're seeing machine vision being successfully integrated into broader systems and exchanging useful data? It's something you touched on earlier, I think.
Yeah, I'm sure. Yeah, to perfectly, follow on and tie with what Carsten's just been talking about, and the idea of a system now, or the vision system itself, now becoming more of a sensor, more of a all-encompassed part that's installed to give everything that's needed is definitely obviously where we're going. A few examples that you've asked for there. I mean, if we think about a couple of different industry sectors, so if we start off with let's say the logistics sector, we think about something called AMRs, autonomous mobile robots, which are becoming more and more used within various different areas. It's another one of those perhaps buzzwords. And with what Carsten's talking about in terms of looking at the way that industry has been using communication protocols and its language, for want of a better word, and vision technology, up until recently has been using its own language, let's say, and now we can put something like a simple vision sensor, let's call it that, into something like an autonomous mobile vehicle, an AMR, a mobile robot, and the information about where is it for navigation purposes, where's the object, oh, there's something in front of me, I want to try and avoid that. All of that information is sent back to the controller of that vehicle to understand in its own language, because we're now talking the same language. So there's an example there. I think Sean mentioned agritech earlier on, and we've got examples where harvesting vehicles are now recognizing, as Sean was saying, the crops, but also the where to harvest and where not to harvest. And again, because we're now talking in the same language, a simple installed vision type sensor can now give the information to the maybe autonomous harvesting vehicle to say, okay, you're going down that way, and these are the crops you're going to harvest. And then food and beverage, let's say, for example, with regards to quality inspection and inspection on packaging, all of these systems now are becoming more and more user-friendly. I know it's a common term, but to the extent of which, you almost are talking plug and play to say, inspect this item of food to see if it's damaged or not, or inspect this label to see if the use by date is legible or not. That all now is installable, operational and deployable with a minimal amount of fuss because of this useful data and the fact we're talking the same language as the manufacturing system and can reincorporate it in the whole thing.
Great, thanks. Okay, well that brings us to the end of our kind of pre-prepared topics that we've spoken about before. So now I want you to have a look at the fear in our panelists' eyes as we throw some audience questions at them. We do have another 10-15 minutes, so feel free to ask some questions. Let's turn to one of those. So a question here from Fred, who says, Neil mentioned standardization of systems allowing for the acceleration of market growth for robotics. If this is the case, why is the UKIVA standard nearly always behind in terms of features or less performance than camera manufacturers' SDKs? Do you see this changing? So Ian, if I can come to you first, because you sort of answered this subsequently, but I don't know if you have anything to add to that, and then I'll come to you, Mark.
Yeah, basically the manufacturers are always pushing the leading edge, and so therefore all their cameras and their SDK can get the best performance out of their cameras, but it's not necessarily what's become a standard. And as Neil said, once you get it into deployable and robotics, you need a standardization system. So I think the manufacturer's SDK will always be ahead of robotics ones. Now, Mark may disagree with me.
Mark, do you want to follow up on that?
Right, yeah. I think this is a massive, complex topic. The first thing is absolutely. I think we have to differentiate between UKIVA is a physical stand. It's a physical and a protocol standard. An SDK from a manufacturer can still be using the UKIVA protocol to communicate with its camera, but it has its own API to control it. Okay, what we're talking about here is called GeniCam, which is the standard that defines how you control the camera, what parameters you can get to it. And we're getting to the stage now that something on GeniCam it's independent of the physical. Is it UKIVA? Is it USB Vision? Is it CoExpress? That becomes irrelevant. If you've got one particular application, you're never going to have to change it. You can say, right, go with the manufacturer's SDK. But by doing that, of course, there's a lot more development work if you need to move away. Maybe that camera has a specific feature that you really need to have, and it's not dealt with in the standards. Okay, then you need to go with it. But if you go with a more of an open standard SDK, you can then move manufacturers, move interfaces, and it gives you more standardization in freedom. And I think it is, you're right. If you're right at the front, you know, if we go back right to the beginning, every camera needed a custom cable because there was no standard of connector to the frame grabber. You know, everything had to be designed. That prevented the growth of the industry. The standardization on cables, USB and UKIVA and Ethernet, has enabled cables gone. There's no issue. There's not such an issue with cables anymore. And it's the same with the software. It's just an evolution. If you're going at the bleeding edge, yeah, your SDK, your camera is going to have a special feature that is not dealt with. That's life, I'm afraid.
Okay, Carsten, did you want to come in on that as well?
Yeah, I mean, I'm with Ian here. I mean, there is innovation in the camera manufacturers area. And as long as the standard, and as Mark said, GeniCam and UKIVA allows to bring in innovation, that's fine. So we can compete on bringing innovative features into cameras and SDKs. And then it's, I think, a natural process. Then over time, these innovations, which will become useful and broadly accepted also with many camera makers, they will become part of the standard. It's a pretty natural process. So in this sense, it's natural that the development in the camera area will always be ahead of the standardization then as a common denominator. Yeah.
Okay. Another question has come in here. So I think this relates to the part of the conversation where we were talking about illumination. So the question is, are we talking about free air scenarios only, visible, and under what conditions? There are other applications as well, such as subsea. So Boris, I think you were going to come in on that one.
Yeah, happy to do so. And if I don't cover everything that was mentioned in these 3 different questions, please feel free to reiterate that and put more details into the Q&A. But from what I see, and if I get this right, what's written here, I have a few comments on that. So first of all, if you are working in the outside world with sunlight, that's already quite nice in terms of the spectrum you're using. It's fairly equally balanced. There are no spikes. So this is also what Mark mentioned. That one of our concerns when you work with LEDs that try to mimic sunlight is if you have there's usually a huge peak in the blue. And of course, the main intention is to transfer and convert all of that blue into the bright spectrum that mimics the sunlight, but you will have a remaining peak in blue. And that might cause you some problems because this is sometimes for some LED, this is very far in the blue and not all optics can handle that. So that's just a comment on the fundamental difference between LEDs that mimic sunlight and sunlight itself. However, if you are working in the sun, then stray light is going to be your biggest enemy. Yeah? Is the sun in your field of view, you're up for a lot of trouble. But even if the sun is not directly in your field of view, all of a sudden some crazy reflections can cause all kinds of artifacts. So this is really a big challenge when you work outside. I hope that answers some of your questions in that first part. And then the second part of that question is, are there any subsea applications? And spontaneously, I can mention two. The first one that I saw in the last couple of years was people that are from the academic world and they are trying to measure plankton density. I hope it translates to plankton in English. And then another thing would be if you travel throughout Scandinavia, say Norway, there's a lot of people that, how do you say that? They grow salmon, there's salmon farms, right? And these people have a big interest in monitoring them and getting a sense of their weight. So they use 3D metrology to in situ measure and see how does their livestock develop and are they all healthy, down to the details of are they having lice actually. So even sickness or illness you can detect with these kind of systems. And that would be two quick examples for subsea applications. I hope that was helpful.
Great, thanks. If any clarification, do pop that question in again. This is a really interesting question. So does the panel think our known machine vision industry will fragment into smaller specialist end applications and supplies in the future? Will these markets needing special and specific rather than off-the-shelf standard components? Neil, can we come to you first on that one?
Sure thing. Thanks, Warren. I'm not so sure about fragmentation in terms of the suppliers being maybe a bit niche, but I think it links back to a little bit of what I was talking about before. Perhaps the hardware itself may become a little bit more generic in certain ways, but the software behind solving the applications will be more out of the box. For example, here's a bit of software to solve a robot problem. There's a robot issue, a robot guidance for pick and place. Here's one for agri-tech that helps crop identification and harvest guidance. So I think the fragmentation may be, if you can call it that, more a case of there'll be more specific out of the box solutions, almost like apps for your smartphone. If that you say, okay, I want to do some robot guidance, or I want to do some mobile vehicle guidance, or I want to do some label inspection or some quality inspection specifically to food or to manufacturing or to automotive. And I think those sorts of solutions some of them are here now, but a lot of them now will be brought on to solve specific tasks to make out of the box vision solutions more configurability a way of the future. And that's my view.
Okay, Carsten, do you want to add to that?
Yeah, I'm with you, Neil, on this one. I mean, I think we will see consolidation rather than fragmentation in the industry. I mean, remember 5 or 6 years ago what happened with the sensor, the camera sensor, imaging sensors industry, how many acquisitions we have seen. And I believe we've seen some acquisitions also in the vision industry. And I think this will go on, and I believe there will always be at the edge of the larger mainstream market, there will always be a room for specialized smaller suppliers or vendors. But I think in the mainstream, through the standardizations we've discussed, and through the hard and software, we'll see consolidation, growing company sizes, but getting less or fewer of these. So I think that's a natural habit happening in a growing industry. Yeah, that would be my view on this.
Sure. Okay. Thanks. Another question that's just come in, which is a sort of variation on a theme, is that do we see that more end users will develop their own applications rather than working with integrators? So are integrators themselves under threat? Mark, do you want to take that one?
I think integrators aren't under threat, and if we go back 20 years, it was the same situations. You know, smart cameras came along, made it simpler, the whole concept of making stuff easier. But if you're going to make it easier for a complete novice, when you say an end user, is that an end user that is vision capable, has an understanding, or knows nothing? There's already graphical software for easy programming of solutions. You still need to, a lot of the time, you still need to understand the lighting and things like that to build those. So certainly simple applications we've already seen, but what that's labeled is applications that would be too expensive to get an integrator in to do, so you could realize them. If we go to the very low end, let's say ID reading, that's got to the stage where you've got a specialist camera with lights that grab about 20 different images with a liquid lens on it to do the focus. All's done automatically. You point it and it grabs an image of a barcode. That's a solution there. The actual integration in that is quite incredible. But then at the high end, you've got big complex systems. You're always going to need an integrator that really understands what they're doing. So I think as you go up the complexity, more and more simple things can be addressed with simple off-the-shelf. And if it's a big application like code reading, companies will go and develop a very specific solution, which was really addressed about that fragmentation. That if there is a market where it fits, that is a large market and lots of people have a demand, then companies will produce a very specific solution that an end user can just bolt on the production line, press a button, and get the answers they want.
Okay.
Yeah.
Ian, did you want to comment on that a little bit? You had a comment to make there?
Yeah, well, I think there's going to be also some companies becoming more specialist in particular vertical markets. So they become experts in particular areas and then just do that rather than full integration. So whether that's an end user or an integrator is up for debate. But I think there'll be more companies specializing in smaller vertical markets.
Okay. And Carsten, you had a comment to make as well there.
Yeah, I agree with both of you. What the trend we have seen is it's about the size of the end customer, because when you run 20 manufacturing plants around the world, you most likely have the manpower to develop understanding of vision, and then more likely you also engage in endeavors designing your own system and your own vision. While for smaller end customers, I can see they continue to rely on system integrators, definitely. Yeah.
That's a relief for many of our people listening to this, I hope. Okay, let's begin to wrap up now. And I just want to ask the panelists to kind of fast forward maybe 5 or 10 years and think about the sorts of technologies or applications that might have opened up between now and then and what we'd be excited about, what we'd be talking about. Mark, do you want to come in first on that and think where we might be?
Yeah, absolutely. So I think what you hear as the buzzwords in the new exciting things that are coming along, or you see deep learning, embedded vision, hyperspectral imaging is one. All of those, and I didn't mention 3D vision here because 5 to 10 years ago, 3D vision was the buzzword, but the reality was there wasn't much being sold in 3D vision. Okay, and it then takes 5 to 10 years for this make it easy, make it click and point and click that anyone can do. Then you start to get the big things. So the revenue in 3D machine vision is now a significant part of machine vision, whereas 10 years it wasn't. But everyone was talking about it 10 years ago. And I think we're seeing exactly the same thing here. Deep learning, yes, it's getting traction. Everyone's talking about it, but I bet you at the moment, the numbers compared to the traditional, it's still relatively small. And I say hyperspectral imaging is even further away. It's expensive technology. It's very hard to do. But that will change. There's a lot of innovation going on. So there's what I see will happen. Make it a reality. Most of the hyperspectral systems we're selling to as research is, will it work? Will it solve my problem? Yes, you might get the lucky win, but it's not selling into the mainstream yet. Okay, and what's after that? Well, we're here because we'll be talking about it next year or the year after, because it'll be another buzzword. There's nothing in my eyes that's newer than those two buzzwords at the moment.
Okay, that's great. That's interesting. Sean, do you want anything to add to that?
Yeah, I think I agree with Mark on much of that. I think sensor manufacturers are lowering the cost of some of their multispectral sensor availability, so hyperspectral or SWIR or UV specifically. But it's still not a low-cost application. It's still a high-end investment. So I think as the cost of that technology lowers, there'll be more realistic use cases for that in industry. I think on the deep learning side of things, it Mark's right again there. I think it's definitely a buzzword at the moment, and there's not the depth of understanding as to where deep learning can add real value over typical machine vision classification tools. I think going forward, that understanding will deepen the same as it did with 3D and where that sits in the analysis chain. And I think the simplicity of implementing deep learning will be improved as well. There are solution providers providing the one-stop shop, as it were, now for the labeling, the classification, and then the inference on the edge on the camera itself as a kind of out-of-the-box package. So simplicity there is certainly coming, I think.
Okay, great. Carsten, any view from you?
Yeah, I think for me, there are two driving factors which kind of, for me, count as indicators what will become successful in the future. I mean, one is definitely being able to approach new areas where you failed in the past. And like already said by all of you, 3D was the big buzzword 10 years ago, and it has proven to be such a kind of criterion indicator. And here deep learning for me falls into this category. We'll see deep learning in a lot of applications very successfully tackling challenges we couldn't solve in the past. But there's also a second indicator from my view, which is a commercial attractivity. And here for me, embedded vision will definitely fall into this category, because once you have an embedded vision system which is solving your problems, you don't need the modularity, you don't need the supreme processing power you have with a PC with 15 GPUs or whatnot, you will pay a third of the money for this vision system. And this will be attractive for a lot of end users and also system integrators. It will be very disruptive in my view, embedded vision. And we've just seen the lights of the train coming around the corner in a mile's distance, but it will be there and it will be fast. Yeah. Thank you.
Okay, thanks. Neil, over to you. Any comments on this?
Sure, yeah, thanks. Obviously, I agree with pretty much everything everybody else has said, and I don't want to repeat that, but the three main things I had in my mind were with regards to the deep learning technology, and I think Mark touched on it earlier when he talked about anomaly detection. I think, and as Sean has just mentioned a few seconds ago, the ability and the accessibility of that for people who are even down to the potential novice end is going to be greatly improved and greatly more accessible. Second thing is robotics. I talked about it a little bit earlier, but not so long ago, the UK, for example, dropped out of the top 20, I think, of its robotization per capita in terms of our usage within industry. And that is only going to go one way, and that's going to be upwards because of the various things that have happened in the last couple of years. And I think the robot guidance and robotization in combination with machine vision and those applications are really going to start to get bigger and bigger and more usable and more accessible.
Great, thanks. And Ian, you has a view on kind of where application market's going to open up?
Well, I agree with all the others, basically, that I think lots of the products that are in R&D at the moment and things there will be more application areas come open for them. Things like, as Mark said, with the hyperspectral imaging and Sean said about SWIR imaging. So using different wavelengths for part of classification, the costs will come down and the application areas will increase. So I think that the use of non-visible or non-standard RGB will increase over the next few years.
Okay. And Boris, just so you're not left out of this last question, so have you anything else to add other than you agree with everything anyone said?
Yeah, this is a difficult one now, right? Being the last one to talk here. I think I essentially agree with what you guys said. To some extent, you guys are also closer to the system level world than I am. But yeah, from everything I can see, it always takes this industry like 5 to 10 years to go from, hey, this is here, like at the edge, and now it's mainstream adoption. And it'll be very interesting to see how we as a community, as an industry, get used to embedded, get used to AI, see how that replaces current solutions. And the other thing that might be worth to mention is, I think the machine vision industry in general was always very flexible because it's a very, very small industry. It enables a lot of big industries, I guess. But, you know, going back more years, like, you know, whatever, 20 years, or, you know, going back to the time when I wasn't even around in that industry, you know, oh, look, we need lenses. There's these lenses from the photography market with F-mounts. Let's use that. Oh, look, there's GPUs. They can do lots of cool things. Let's use that. There's frame grabbers. They weren't invented for our industry, were they? Let's use that. That seems cool. We can do stuff with that. And so I'm also very much looking forward about, I would expect that one of the big driving application spaces, right, be it, we touched on those before today, be it augmented reality, virtual reality, be it, you know, all things autonomous driving, autonomous trains, autonomous drones, whatever. Agriculture is a big thing. I'm really looking forward to what kind of disruptive piece of technology is developed in one of these very specific fields that we as an industry can conduct, can use and bring it to the worlds we already serve today, like the factory automation, like the 3D world, and all these applications that were already discussed. I guess that's all I can add as person number 6. Or so yeah, that's it from my end.
Great, thanks very much. Well, that's a good place to end the conversation. So just remains to say thanks very much to all of our panelists. That's Mark, Carsten, Sean, Ian, Boris, and in particular Neil, who's done much of the heavy lifting in preparing the team for today. Also thanks to Matt Chappell at the PPMA for producing today's webinar. Finally, thanks for your questions and for being with us today, and a reminder to fill in the post-event survey in a moment or two when the broadcast ends. Thanks very much and goodbye.